Nanomaterials to give you a presentation on the synthesis of nanomaterials. We are Yixin Liu and Jian Ren, and we both from chemical engineering. Here is the outline of today's presentation. According to the dimensions of nanomaterials, we have divided our presentation into three parts. First is a zero-dimensional nanostructures, and second is a one-dimensional nanostructures, including nanowires and nanofibers. The third part of the presentation is a two-dimensional nanostructures, including separating, atomic layer deposition, and Langmuir boundary fields. Now let's start from the first part, nanoparticles. Here is the picture of several kinds of nanoparticles. We can see metal particles, polymer particles, and particles in the medicine. And here, this is the synthesis of the semiconductor nanocrystal. We can see by injecting the precursor into the flask, the reaction starts, and then the precursor decomposes in and nucleing into the growth of nanoparticles. And as the size increasing, it can be seen from the color change.
So there are other ways to make nanoparticles. One of them is use micelles as a template to fabricate nanoparticles in the microemulsion. And the micelles are the aggregate of surfactant molecules, which are generally the one with one head of the hydrophobic head and the hydrophilic head and hydrophobic tail. And in the long polar solvent, the hydrophilic head will form the core, and the reactant in the aqueous solution will in the core and form the nanoparticles.
Okay, let's move on to the one-dimensional nanomaterials. And the one-dimensional nanostructures including nanowires, nanorolls, and nanofibers. I would like to show you the Spaniard's growth of nanowires. The most powerful way of Spaniard's growth of nanowire is the vapor, liquid, and solid nanowire growth. We can see the idea is that we take a nanoparticle as the catalyst and then grow nanowire from it. We can see from here the silicon nanowire is grown from the gold nanoparticles. And to better understand the mechanism of this progress, let me show you this video. We can see here a gold nanoparticle is laid on the surface of the silicon substrate. And this system is heated up to about 400 degrees C, and also we pass ethylene gas as a precursor into this system. The ethylene gas dissociates into silicon gas and hydrogen gas, and the silicon gas is absorbed by the gold particle, and the hydrogen gas leaves this system. So we can see from this phase diagram, the gold particle is melting into the gold silicon liquid alloy. And then if we keep on adding silicon gas into this system, and the silicon will be super saturated and nucleate, and then form to the growth of one-dimensional nanowires. So we can see here is the silicon nanowire growth.
Electrospinning is a technique we can use to make nanofibers. First, we can see we need to dissolve the polymer in the solvent and make the precursor solution and plug the solution in the syringe. And we can supply a high potential between the needle and the collector. The high electric field will stretch the droplet and form the Taylor coil. And this is the point where the steam jade will erupt from the surface to form the nanofibers and collect on the collector. Now let's look at what happened on the tips of the needle. The fibers are generated. And this is nanofibers goes down along the collector. Recently, there's another new technique named the nanospider, which can string nanofibers without needle. And from the video, we can see there's a positive charge on the polymer solution and a negative charge on the top. And the high voltage, the electric field will drive the polymer solution to spin the fiber and collect on the top. There are a lot of advantages of the nanospider. Compared to the nanospinning, it can make nanofibers in large scale, and it will also have the easy maintenance.
And now let's move on to the third part, two-dimensional nanostructures. And there are several major methods to synthesis nanofilms, like we list here. But today we would like to show you only 3 of them, that is sputtering, atomic layer deposition, and lamellibranch films.
Sputtering is a technique we can use it to coat the surface and deposit the thin film. And usually we have argon gas at very low pressure in the vacuum chamber. And after applying high voltage, the gas will ionize, and the energetic gas will knock the atom or molecules of the target and deposit them on the substrate. And this is the process of the ion beam sputtering. Ion beam sputtering is a method. It have a separate ion source, and the ion leave the source, and it will neutralized by the electrons from another external filament. By using different targets, we can deposit a multi-layer film.
Here, atomic layer deposition, ALT method can provide the best possibility of controlling the thickness and the surface smoothness of the nanofilms. You can see here, this is a 3-dimensional matrix of the coating. And on the surface, we have hydrogen, high hydroxyl groups, and the TMA poles will react with the group on the surface to form the first atomic layer. And then, as we have water poles, the water poles will react with the first atomic layer to form the second atomic layer. And then, layer by layer, we can get the nanofilms with uniform thickness in every gaps, corners, and 3D structure.
Button films are composed of the amphiphilic molecule, which have a hydrophilic head and a hydrophobic tail. And by immersing the solid substrate in the liquid, we can transfer the monolayer film to the solid substrate. And it can be the vertical deposition or the horizontal lift. And by using different deposition methods, we can get different structure of the films with desired structure and thickness. And the LB film are named after Irving Langmuir and Catherine Bartlett. And this is a short film extracted from the documentary Langmuir's World.
In the last few years, we found that we can transfer these thin layers of thin films or single layers of molecules from the water surface onto metal or glass plate.
Langmuir's partner for the work on surface films was Dr. Catherine Blodgett. Together, their investigations produced films that would be used as non-reflective coatings for everything from camera lenses to eyeglasses.
You'll see that the reflection is troublesome from the uncoated glass on this side, but it's not at all troublesome from this lens over as far as this line of demarcation. When I turn my head away from the light, both lenses appear the same.